Hey everybody, I'm going to work out the Chapter 9 guided problem for you. Let's just take a look at it. Suppose the coffee industry claimed the average adult drinks 1.7 cups of coffee per day. To test this claim, a random sample of 60 adults was selected, and their average coffee consumption was found to be 1.85 cups per day. Assume the standard deviation for daily coffee consumption per day is 0.5 cups using an alpha of 0.1. Okay. So the first thing this thing wants us to do is determine our null and alternative hypotheses. Remember, the null hypothesis is the status quo, the way things we think they are, or the way we're claiming that they are. So that's going to be right here, where they claim the average adult drinks 1.7 cups per day. And then we have to decide, are we testing for a change, that it is no longer 1.7 cups per day, but it is something else? Or are we claiming or testing for a specific change, like it's gone up or it's gone down? So you have to read the language of the question very carefully. So all they're saying here is, suppose they claim this 1.7 and we're going to test the claim. So that means that we're testing to see whether it's gone up or gone down, and that's how we can decide that this is an equal to and a not equal to, as opposed to if we were testing if it was just going up or not going up. So our null hypothesis is that our population mean is going to equal 1.7 cups per day, what the industry claims it is. And then our alternative hypothesis is that it is going to be less than 1.7, or sorry, not less than, not equal to 1.7 cups per day. So there, whoops, I've got my zoom control there and it gets in the way. All right, so now we have to calculate our z-test statistic. So the easiest thing for me to do is to start with just all the information I have. So the claim or the status quo, I just call it null to make it easy for me. You can use a term that works better for you, is 1.7 cups per day. Our n, or sample size, is 60, because that's the number of adults we're sampling. And our x bar, or our sample mean, is 1.85. So out of those 60 people, our average was 1.85 cups per day. We have a standard deviation, and this is not the standard deviation of the sample. It just says the standard deviation of coffee consumption. So that's the population standard deviation, is 0.5. And our alpha is 0.1. So that's all the information that we have. So to calculate our z-test statistic, we're going to use the formula that's provided for us in the book. Also, if you forget it, you can always go to question help and do view an example, and it will give you the formula right here. Okay? Or if you've just done it a bunch like me, you kind of have it memorized at this point, but I don't expect everybody would, right? So our formula is our x bar minus our null. And then we divide that by the population standard deviation over the square root of n. So there's our z-test statistic. They want us to round it to 2 decimal places. Now it wants us to calculate our critical z-score. So our critical z-score is just really the z-score of our alpha. So when we're doing a two-tailed test, which means we're testing whether or not we're equal to or not equal to. Think of the normal curve. I wish I had a picture of it for you here. I don't. A two-tailed test means whether it's, you remember that normal curve, and the either end of that curve, if it's to the extreme of either end, we're going to say, hey, that's too far away from the mean for us to conclude that the mean is still 1.7. So when we take our sample and we get the mean of that, right, and then we find the z-score of that sample point, that's our z-test, we're asking ourselves, is that far enough away from the mean, either above it or below it, because this is a two-tailed equal to or not equal to test, that we can conclude that there's been a meaningful change in the population mean. Okay, so the critical Z then is the line or the marker that we decide is where our Z test has to be further away from the mean than that. If that happens, we're going to reject the null hypothesis and accept the alternative hypothesis. And if our critical Z is not further away, so closer to the mean than the Z test statistic, then we'll accept the null hypothesis and reject the alternative. All right, so to find our critical Z, I'm going to take the absolute value of norm.s.inv of the alpha divided by 2. Why divided by 2? Because it's a two-tailed test, or our rejection region is going to be on either end of that normal curve. So that's my critical Z score. Again, it wants 2 places. Uh-oh, let's see what we did wrong here. Well, for one thing, that's weird. It rounded weird, right? 1.645 should round to 1.65. You know what else though it's going to want is, because this is a two-tailed test, it wants us to do negative 1.65 comma 1.65. Again, I've got my zoom controls in my way. Let's see. There we go. All right, and then it wants us to interpret this. So because my Z test is further away from the mean, or outside of that range of negative 1.65 to 1.65, I'm going to reject the null hypothesis. So because the test statistic does not fall within the critical values, in other words, it's further away from the mean of the distribution than the critical Z, I will reject the null hypothesis. And then it wants us to determine a p-value for the test. P-value is just another way of saying what's the probability of getting a result as extreme or more extreme, or in other words, as far away from the mean or more further away from the mean than my test statistic. So I'll just use norm.s.dist, and I'll do my Z test, and then I'll say true. Remember that when I do norm.s.dist, it's giving me the probability of everything from that point, so 2.32, Z score 2.32, to the left. But I am testing to see if it's how far away that point is from the mean. And so if I have a positive test statistic, to find the probability of it, I'm going to do 1 minus that p-value. If I have a negative Z test statistic, I will just do the calculated value with norm.s.dist. Because again, we're measuring how far away that point and anything after it is, the probability, not how far away, of that point or anything to the right or greater than it is with the p-value. And then the other thing is, if my p-value is greater than my alpha, in this case, see, it's less than my alpha. So if my p-value is less than my alpha, I'll reject the null hypothesis. And if my p-value is greater than my alpha, then I will reject the alternative hypothesis. So the p-value is, oh, but you know what? I almost forgot something. So this is a two-tailed test. So this is the probability of getting a point to the right of Z of 2.32. But I need the probability of getting to the right of 2.32 or to the left of negative 2.32. So it's going to be this times 2. That will be our p-value around to 3 decimal places, 0.02. Okay, so there's the first one. The second one is really similar to it, but I'm going to go ahead and I'm going to delete everything so that we can walk through the process again. What's different about this one is we don't have a population standard deviation, so we're going to have to use a sample standard deviation. and then use the t-distribution rather than the normal distribution. So suppose the average size of a new house built in a certain county was 2,273 square feet. A random sample of 25 new homes built in this county was selected in 2018. The average square footage was 2,195. Sample standard deviation is 224, complete parts A and B. All right, so first of all, figure out, we're going to use this in alpha 0.02 and decide whether or not this provides evidence to conclude the average house size has changed. So again, it's not asking if it went up or went down, just changed. So because of that, we're going to say our null is that it's equal to, and our alternative is that it's not equal to, and then it's going to be this claim here, or in this case, it's what the average was in the past. So 2273. All right, now to figure out our critical values and things like that, I'm going to go ahead and just start with the information I know. So my null, or our past belief of what it was, is 2273. Our n, or sample size, is 25. Our x bar, or our sample mean, is 2195. And our sample standard deviation, or S, is 224. And our alpha is 0.02. All right, so that's everything we know. So this one asks us for the test statistic first. Again, we'll be using the t because we have a sample standard deviation. So I'm going to go, this equals t dot INV. My probability is going to be, because it's a two-tailed test, okay, it's going to be my alpha divided by 2. And then my degrees of freedom is going to be n minus 1. And it's always n minus 1 for these problems. So there's my t-test statistic. Now this is weird, this is a quirk of Pearson, but I remember on this problem that even though this is two-tailed, so it should be negative 2.49 and positive 2.49, for whatever reason, they want us to use just this negative, I believe, or maybe it was just a positive, we'll have to look. But really, anytime it's a two-tailed test, then our test statistic is going to be a negative and a positive, always at the same number. So the first thing we have to decide is this the t-score of alpha, or the negative t-score of alpha, or the t-score of alpha divided by 2. And so when we have a two-tailed test, it's the t-score of alpha divided by 2. I'm going to try just the absolute value of that, 2.4. Oh, it wants 3 decimal places, so I better 2.492. Yeah, so wanted the absolute value of it, which is a positive number there. Okay, so remember that this is really plus and minus that. So now it wants us to do our, I'm sorry, that wasn't our t-test statistic, that was our critical t. Our t-test statistic, we're going to use the same formula we used in the last problem, except instead of population standard deviation, we'll use sample standard deviation. So the numerator is x bar minus our null divided by our denominator, which is the sample standard deviation divided by the square root of n. So our test statistic is negative 1.741. I only wanted 2 decimal places. You got to read it carefully, don't you? There we go. Now we state our conclusion. So in this case, our test statistic, our critical value is plus or minus 2.492. And our test statistic is negative 1.741. So it's within the range of those critical values, okay? So we're going to not reject the null hypothesis because there is not sufficient evidence to conclude that the average house size has changed. Now look, we could fall into the trap of choosing increase or decrease, but we were testing for just to see if it changed, not to see if it increased or decreased. Okay, and in this case, right, our sample actually was less than our null, so that would lead us to believe, oh, maybe the population sample or population mean has gone down. But because it's only gone down by this amount, it's not far enough away from the mean, not outside of the critical values, that we feel comfortable rejecting it fully. So we just have to say, don't reject it. We don't know. We don't have enough evidence to show that this has really changed. Now it wants us to do our p-value. Again, that's going to be of our test statistic. Okay, and so we're going to say this equals t dot dist, because this is negative. Oh wait, what did it want from me? Oh, degrees of freedom, which is n minus 1. Cumulative is true. Remember, this will return to us the probability of a z of negative 1.741 or less. So when we have a negative test statistic, then we just take that number. We don't have to do 1 minus it. When we have a positive test statistic, we have to do 1 minus it. And then because it's two-tailed, we multiply that by 2. That's it. Okay, last problem. Aren't you glad? All right. Consumers with credit scores below 600 have very difficult time getting approved for car or mortgage loans. Historically, 17% of people had a credit score below 600. Due to the recent financial crisis, the federal government is concerned that this proportion has increased. So now we think it's increased, right? So that's going to change our test. To test this hypothesis, a random sample of 500 people was chosen. And from this sample, 107 people had credit scores less than 600. Use alpha of 0.1. So I'm going to start with all the information I know. Again, don't get confused by the credit scores. Those aren't the data we're looking for. We're looking at the claim. The null is that 17% has credit scores below 600. Let's see. We have a sample size, n, of 500. And out of that sample, X is 107 people actually had credit scores of less than 600. So our sample proportion, or P bar, is going to be X divided by N. All right, so in our sample, 21.4% of people had credit scores of lower than 600. All right, and then we have an alpha of 0.1. So the first thing we have to do is determine our null and alternative hypotheses. And so remember, our null is that it is, so in this case, we think it's gone up, okay? So our null is that it will be less than 0.17 or equal to. And then our alternative is that it will be greater than 1.7. So we're testing to see, is it now greater? Did it go up? All right. So we have to determine our critical values. So critical, we're back to using z-scores instead of t's, because that's what we do with proportions, okay? So our critical z is going to be equals norm I and v. I'm sorry, norm dot s dot I and v. And then our probability is our alpha. Now, in this case, we don't do alpha divided by 2 because it's only a one-tailed test. So if our alpha is 0.1, then the probability of that happening, again, this is going to return me a negative, so I have to do the absolute value of it. It's 1.282. Only wants 2 decimals, 1.28. There's my critical z. My test statistic, sorry, z test. So this is another one, like, so I don't remember the formula to this, right? So what's cool about that is I can go here to question help, give you an example. It will give me a formula that I can then use, okay? It's kind of complicated, but not too bad. So our formula is our P bar minus, whoops, I think I messed that up, Control Z. Equals P bar minus the null, there's our numerator, divided by the square root of the null times 1 minus the null divided by n. There's our test statistic. 2 decimal places, so 2.62. All right, so our test statistic is greater than our critical value, which means it's further away from the mean than our critical value. So we will reject the null hypothesis and say there is sufficient evidence that the proportion of people with credit scores below 600 has increased. Quite a bit, it looks like, right? But it's hard to tell from just one test. Then to do a p-value, again, we use norm.s.dist. We use our z-score. True. Remember, that will return to us the probability of getting a value less than that, but we want the probability of getting a value greater or further away from the mean than that. So I'm going to do 1 minus that. And in this case, we don't have to divide by 2 because it's only a one-tailed test. So 0.004. That's my p-value. And that's it. So hopefully that wasn't too horrible. And hopefully, hopefully it will help you do well on the assignment.